Okay, so today's lesson's on section 3.2, differentiability. There are 4 ways that a function is not differentiable at a point. And these are very important to know. So there's 4 ways that a function is not differentiable at a point. So a function will not have a derivative at a point, f of a, where the slopes of the secant lines fail to approach a limit as x approaches a. So basically, here are the 4 different ways. A corner. So for example, the best example I can give you here would be like an absolute value function. If you look at an absolute value function, it's a v, and if you look at this function, it has a corner right here at 0, 0. So f of x, absolute value, is not differentiable at x equals 0 because the left-hand derivative does not equal the right-hand derivative. The left-hand slope is not equal to the right-hand slope. A cusp. I call these a cusp. I think of them as little birdies. Do you remember even over odd? We talked about these in the first chapter as a refresher of types of graphs. So a cusp is where the slopes of the secant line approach infinity from one side and negative infinity from the other side. So basically, this is an example of a cusp. We have this bird-like shape. Even over odd functions will give us a cusp. A vertical tangent. This is where the slopes of the secant line approach either infinity or negative infinity from both sides. So for example, if you look at the cubed root function, the cubed root function right here has a vertical tangent at 0. That slope goes pretty much vertical. So the slope would be undefined, which means that we couldn't have a derivative. And then finally, discontinuity. If a function's discontinuous at a point, then the derivative is not going to exist. And we kind of already talked about that a little bit. So we know there's other types of discontinuity. This is an example of a jump. Don't forget that a removable discontinuity. So we can have a removable discontinuity, and that would be not differentiable. We could have an infinite discontinuity and a jump. Anytime that there's a discontinuity, there will not be a derivative at that point. So these are critical. You'll need to know these the rest of the year. There's 4 ways that a function's not differentiable at a point. At a corner, at a cusp, at a vertical tangent, at any discontinuity. Those are where a derivative does not exist. So problem 1, find all points in the domain of f of x where f is not differentiable. Well, right away, I look at this problem and I see absolute value. And I know absolute values are v. So when I look at this, I remember x minus 2 inside the bars tells me that this graph is going to move right 2 units, and this plus 3 tells me it's going to move up 3. So if I sketch this, right 2, up 3, there's my point. I have this absolute value. So this function is differentiable everywhere except at x equals 2. So at x equals 2, f of x is not differentiable because of the corner. The left-hand derivative doesn't equal the right-hand derivative. Locally linear. Okay, this is fabulous because we're saying that differentiable functions are locally linear. And what that means in plain English is if I take a function and I zoom in, every point that I zoom in on, as I zoom in closer and closer and closer, if it goes to a straight line, if it starts straightening out, then it's differentiable. So let me show you on my calculator what I'm talking about. If you look, hopefully you realize that a quadratic, x squared, is going to be U-shaped. And that's not a V, it's not a corner, it's not a cusp, it's not a vertical tangent, it's not discontinuous. So when I look at these, I'm going to be able to show you that they're going to straighten out. Okay, so here I go. I got my screen captures up here for you. The first one that I have here, this is my function x squared minus 2x plus 3. And this is the original graph if I just go graph it at negative 10 to 10. Now, as I zoom in, so each time I zoomed in more and more, and you can see as I zoom in, do you see that that U is straightening out? It's getting to be linear. This is called locally linear. Since this function is locally linear at that vertex, it's differentiable. Now, on the other hand, when I take the absolute value of x, here's negative 10 to 10, but as I zoom in, and I know it doesn't look like I am, but I really am zooming in here. As I zoom in, nothing is changing. This is not locally linear, hence that's why it's not differentiable at 0. That's what they're talking about when they say locally linear. We can zoom in on a point, and if the further we zoom in, the more it's going to resemble a line, and eventually it'll straighten out completely as we zoom in. Okay, problem 2. Tell why each of the following is not differentiable at x equals 1. Tell if it's a corner, a cusp, a vertical tangent, or a discontinuity. So part A, y equals 1 over x minus 1. I hope you all remember from the first unit that this is going to be one of those inverse functions. This tells me that I'm going to move right 1. So if you remember, that means that I have a vertical asymptote here, and we get this graph. So why is this not differentiable at x equals 1? Not differentiable at x equals 1 since infinite discontinuity. At x equals 1. If we think about the limits, the limit as x approaches 1 does not exist. We're going to negative infinity and positive infinity. Those are not real. So that does not exist. Part B, absolute value again. Hopefully you already know what's going to happen. But again, this tells us to move right 1. So when I sketch this, we all should know that absolute value is a v. I get this graph. So this is not differentiable since there is a corner at x equals 1. And this means that the left-hand derivative, the left-hand slope, does not equal the right-hand slope, right-hand derivative. And letter C, cubed function. This again is moving right 1, but the cubed root actually has a vertical tangent. So we're going to move right 1, but now we look like this. You can confirm these graphs on your calculator if you don't agree with me. But this one has a vertical tangent at x equals 1. So it's not differentiable. Okay, now I'm going to show you how to do the derivative on the calculator. Don't get too excited because you are not going to be using the calculator all that often, but I hope you can see here that this is pretty complex. Don't cross those directions out because now the two TI-89 calculator directions are different. If you look at your calculator, you're going to hit second 7. And if you look at your calculator, there's a little d that's in cursive, and that means derivative. So you're going to have the d in front, second 7. Then you're going to type in your function, comma x, close your parentheses. Then we're going to put that bar in that I showed you before, x equals negative 2. So I'm talking about problem 1 because it says find f prime of negative 2. So we're going to type this function in our calculator, put a comma x, and then we'll put bar x equals negative 2. This is what it should look like on your calculator, right here. When you hit second 7, oh, I put the wrong thing. That's not good. Okay, scratch what I said. It's not second 7. I got ahead of myself. It's second 8. Second 7 is what we'll learn in the next units. So second 8 is the derivative, the lowercase or the cursive d. And look, I typed in our function 3 caret x plus 5 in parentheses times x squared, comma x, close my parentheses, bar x equals -2. Then what we'll do is we'll hit enter. And you can see now when I hit enter, I get this nice long drawn out information. This isn't my answer. So what I want to do now is hit diamond enter and get a decimal answer. Okay, so now you can see that I hit diamond enter and I get an answer of 10.6501271762. And if you remember, I've told you before, we're going to use 3 decimal places when we do this. So this tells us that f prime of x of -2, f prime of -2 is going to be -10 point, positive 10, I don't know what I'm thinking, 650. Try that in your calculator, make sure you're getting the right answers, and make sure you change this. This is second 8, not second 7. All of this that I put in here is not correct. All right, and then finally, this theorem. This theorem says that differentiability implies continuity. Think about this. If f has a derivative at point A, then f has to be continuous at point A. That makes sense because one of the ways that we aren't differentiable is discontinuous. This is huge. This is perfect. Because if I ever tell you that a function is differentiable, then that means we automatically know that that function has to be continuous. Now, this does not work backwards. Just because a function is continuous does not mean that it's going to be differentiable. Think about absolute value. Absolute value is a continuous function, but we've seen several times that it's not differentiable at those vertex points. So, if a function is differentiable, definitely continuous. If a function is continuous, you're still not sure if it's differentiable. And then the intermediate value theorem, remember that example that we had before with the woman that gained the weight? So it's just saying that if A and B are 2 points in an interval where f is differentiable, then f prime has to take on every value between f prime of A and f prime of B. It's the same thing. If you have 2 values and you are differentiable, then that means that you have to reach all the values in between A and B in order for that to work. So that intermediate value theorem still stands for differentiable functions. Last thing that I'm going to ask you to do tonight for homework is I want you to take all 5 of these problems and I want you to find the derivative. So I want you, like what we did yesterday, I want you to take all 5 of these problems and I want you to find the derivative of all 5 of them. Then tomorrow you need to come to class with a rule to make this easier for us. I want to know what's the rule, how can we take derivatives without wasting our time and going through all that big limit. So these 5 problems on a piece of paper or on the back of your notes somewhere, and then come up with the rule that we can use to make these finding derivative problems a lot easier.